Okay, hello everyone. My name is Ross Signal. I'm the Director of Product Management and Marketing with Dranitz. I'm joined here in the room by Thurman Bridgers. Thurman did our last presentation. So we are here in our factory in Edison, New Jersey, socially distant, and talking about power monitoring. And this is the third module of our power monitoring seminar series. As mentioned before, we've had several other modules. Our first module was an introduction to power monitoring, which talked about some of the basics. What is power monitoring? What are wiring concerns? What are transducer concerns? Things like that. Our last presentation, I believe that was on the 26th of August, Thurman covered energy monitoring. How do we compare and contrast that to power quality? What are the issues with energy monitoring? What are the basics? What are some of the energy monitoring standards? What's demand? What's energy? Different things like that. Today's focus is going to be power quality monitoring. So we're going to do an introduction to power quality. What is a power quality problem is one of the first things we're going to talk about. Then we're going to get a little geek and talk about standards. We have a couple slides on standards. We're going to look at the IEEE versus the IEC standards, in regards to power quality monitoring, and sort of discuss which applies to you and where you live and what you should be concerned about. Then we're going to look at some of the most common terms when we speak about power quality. So what is a sag or a dip? They're the same thing, just different regional terminologies. What's a swell? What's a transient? We're going to give you some rules of thumb as well on power quality directivity. When I have an event, how do I know whether it occurred upstream or downstream? So we can provide that information for you. And we're going to wrap up today's session with a case study. Here in the Northeast in New Jersey, where we're located, we had Hurricane Sandy come through a little while ago, and it provided some very good data. It came through, affected our factory, affected us personally, but we of course have our monitoring instrumentation, measuring our facility. So we have some very, very good data, and we still recite that data because it relates to everything that we're going to speak about today in the definition of terms, and we have real life information. Our next presentation will be 1 week from today on September 16th, where we continue our power monitoring seminar, and it's going to be on harmonics. We're going to really define what harmonics are, why you should be concerned about harmonics, both measurement-wise and the effects on the power system. What are some of the monitoring standards for harmonics, both domestically here in the United States and also outside of the United States? So in other words, IEC maybe versus IEEE standards, and more appropriately recommended practices for harmonics and rules of thumb. So we're going to talk all about that next week. Our last web meeting in this series will be the following Wednesday after that. I believe that's the 23rd. Well, we'll wrap up our complete power monitoring seminar and do our last module, and that'll be how to do a power survey. So wraps everything together that we've spoken about before, and I've just summarized into the systematic steps on how to do a power survey. And so, whether it be energy, whether it be power quality, what are the steps that you need to follow? So, if you haven't registered for next week's or the final web meeting, please go visit the website that you registered for this presentation, and feel free to do so. And we'll also be sending out reminders, as you probably know. So just a couple rules of thumb here before we get started. I have Thurman here again in the room, is going to help me this morning. So please chat up any questions. I've muted you all because having 70 people speak at one time is kind of a little bit of an issue. So if you do have any questions during the presentation or after we're done with the formal presentation, just drop them in the chat and chat to everyone. And Thurman's going to help moderate them here. And we'll try to stop during the meeting if we see some questions that we can address. But certainly at the end, we're going to address all of your questions that come in on the chat regarding this presentation or anything else related to our products or the industry. So, and again, today's presentation is being recorded right now. Our prior presentations are posted on our webcast page on our website, and this one, by the end of the week, maybe sooner, will also be posted, as will be the subsequent presentations that we're going to talk about. So for those of you who are new to our web meetings here, maybe new to Dranitz, just a little bit about Dranitz Technologies. We are located in Edison, New Jersey, which is where Thurman and I are right now. You can see we're very close to New York City. We're a stone's throw from New York City, less than an hour by train, 45, 50 minutes, something like that. We have a lot of visitors who come in pre-pandemic, of course, and have a trip to New York or the area and stop by our facility. We're right near the main train line. So hopefully soon we'll get back to normal and be able to see you folks again in person. Feel free to stop by. Just give us a holler. We're in a very, very good location here to come visit. So just a little bit about our products and services. We make a line of portable three-phase power quality demand and energy instruments. That's primarily our Dranitz HDPQ family. These are portable instrumentation. We also have a new energy logger and power quality detector called DranExpert, which we'll see a picture of shortly. Thurman introduced that at the last presentation that we had on the 26th. We also make permanent versions of our products and permanent power quality demand and energy systems. So instrumentation that's capable of power quality, demand and energy, demand and energy only instruments, and anything in between. All of our products, whether they be portable or fixed systems or permanent, have their own related software. On the portable side, it's DranView. On the fixed side, it's either our PQView DE or our PQView software. And we do work very closely with our sister company, Electrotech Concepts, who is a developer of PQView and also PQView DE. This is their business, developing and consulting to the power industry. You may not be aware, but we are the U.S. master distributor for our parent company's products, and that company is Gaussen Metrowatt. They make precision multimeters and testers, electrical safety testers, installation testers. We have another sister company who manufactures light meters. That's Gaussen Photo, both industrial and exposure meters and things. And we sell these products in North America. And there's a separate website called Gaussen Metrowatt USA for that. But it's all managed by Dranitz here in New Jersey. It's part of the service portfolio where we take great pride in our technical support. We have free technical support, so we really want you to be very happy with the products, both on, getting up and running and understanding them, but should you have questions along the way. However, there is training available for our products that's beyond the free technical support. So we do remote and also on-site and not in pandemic times, I could say, for training and product commissioning. This is paid for mostly via Zoom today or any other remote web service where we can help you folks on understanding how to properly connect, configure, and then apply our products and get them set up and use them and understand the software. Feel free to check out our website, dranitz.com. It's a continual evolving library of our products in industrial education. Information, as I mentioned before, today's recording or the recording of today's presentation will be posted on our website on our webcast page. I think it's in the support area as we have the prior presentations that we've done in this series. And also, we're proud to say that we are made in the USA. Products that are designed by Dranitz on literally the second floor of our building are manufactured in the same facility on the first floor of our building in Edison, New Jersey. So we take great pride in that, and that really helps us and helps our customers in providing a very prominent or prompt delivery and quality control. So before we get started here, just a view of the products. Here are portable products, our HDPQ Plus family with the SP behind it. This is that new DranExpert product that we spoke about that was announced roughly 2 weeks ago. DranView software. The DranView software works with both of these products. There's different versions of DranView depending upon what product you're working with. And then we have our fixed products, where we have our HDPQ data node, our 61000 family, and a line of energy meters, the AM series meters, and a line of power quality and energy meters, our PQ3K and our PQ5K. All work with either our PQView or our PQView DE software. I mentioned before that we are the master distributor in North America for the Gaussen Metrowatt products, and here's just an example of some of those products, some of their testers. This is a light meter, this is a multimeter, and this is a safety tester that they also sell. So, okay, without further ado, let's get started. So again, today's web presentation is focusing on power quality and reliability. So what is power quality? What are the terms? What are the standards? And how do I define what a sag is, what an interruption is, what a transient is? Just note that a continuation of this will be our next presentation on focusing on harmonics. Harmonics are certainly power quality issues, but they're a little bit different, and so we've separated that into a separate module so we can just focus on those. So the full power quality introduction will be over this week and then next week's presentation. So the first thing is to find, well, really, what is a power quality problem? Different people have different interpretations of what a power quality problem is. So really, for the sake of this, do any of these voltage waveforms present a problem to your equipment or systems? These can be detected by our products very easily, but really it boils down to, do you have susceptibility to these problems? Does this cause, or can this have the potential for your systems to misoperate based upon this? And what we see here, and we'll get a further definition of these things in the coming slides, this happens to be a sag or a dip. This is a transient, maybe caused by a power factor correction capacitor, which we discussed at Thurman's presentation last week. This is a peak transient, a positive transient. This is waveform distortion here, maybe the harmonics that we spoke about, and we're going to cover at our next presentation. This is a swell or an increase in voltage, and this is a long duration sort of sag, maybe a brownout or something like that. So again, it's not the fact that these things occurred, it's the fact that you have susceptibility to these particular problems. You can drive yourself nuts looking for these, but you have to really look at your equipment and systems to see if you will be negatively affected by them. So again, what does that mean? It's really up to your susceptibility. Given the quality of supply, do you have to worry about problems with your equipment and systems? Okay, so that's on a case-by-case basis. As an example, a data center may have higher susceptibility than a simple office environment or something like that. Same thing for high-end manufacturing, semiconductor manufacturing, anything with maybe PLCs or other electronics that are controlling your manufacturing process tends to have a pretty high susceptibility to power problems. And what that usually means is that shorter duration power problems can negatively affect your system. So these are the things, of course, our instruments can capture for you. But again, the more, we'll loosely call it high tech you are and computer and electronic you are, those computers and electronics, adjustable speed drives, things like that, have a high susceptibility to these power glitches and these power problems. So that's really where you need to be concerned. But the most important thing is, what's your economic exposure to those problems? And so do you have a high economic exposure where it can cost you thousands or hundreds of thousands or even millions of dollars in some potential cases if you should go down? Or do you have a low exposure? And the reason why that's important, it's not as much that I had a problem. It's also maybe not the most important thing that I'm susceptible to it, or you are. But it's going to cost me money, either direct money in downtime or issues with my customers, my relationships, whatever it could be. So you have a dollar kind of figure on that. And one of the reasons why that's important, that helps you understand how to mitigate or correct those problems and whether it's worth doing it. If I have a simple plant and yes, I go down once a day, but it doesn't really cost me anything. I press a reset button or do whatever I have to do. There's no loss involved. It's hard to justify economically to your management, to your accounting, that it's worth investing in mitigating that problem. However, in a similar situation, if it costs me $1,000 every time I go down, again, this is very hypothetical, it'll cost me, $500 to fix it or $2,000 to fix it is a better example. Well, that's two occurrences. It's paid for itself at a $2,000 mitigation for a $1,000 problem. So it's simple math, and you'll probably or potentially add zeros to those things, but I hope you get the point in that economic exposure. I've been to industry conferences where they have talks on this, on how technical folks like us, and engineers and technicians and electricians can present this to management in financial perspective so they can justify the release of the dollars or whatever currency that you're in to mitigate these problems. So really, what are the benefits of the power monitoring? And this is just in general, even though we're focusing on power quality here. So certainly problem avoidance. Case studies have shown that proactive power monitoring can increase reliability and prevent failures from occurring by seeing problems before they result into failures. And I think in one of my prior web presentations, I shared that we work with a large government organization who uses a particular brand of UPSs, and they happen to know when the output is starting to fail on those, it throws transients out on the line. So they pick them up with our fix system, and they start seeing these transients. They immediately schedule a service call with that UPS module, so they can take it offline in a proactive or structured basis, because they know if they let it go, it's going to just shut off one day, and you don't know if their protection will kick in properly. So that's the problem avoidance. They are preventing the problem by proactively maintaining their systems using the power monitoring to detect these problems. So also knowledge. If you don't monitor it, you can't measure it. So really you're running blind. You may have power quality issues that are near the susceptibility of your system, the limits that we may be sharing with you later on during this presentation, yet it hasn't crossed that limit. So you're running on borrowed time. So it helps to understand what this is, of course, from a power quality perspective, but also when you talk about energy monitoring as well. So people turn to power quality things to get answers really quickly. And so the first two are proactive, meaning that these are fixed systems usually, which tend to act like a DVR in modern terms for your power system. So you can rewind the tape and see what it's done over the last 30 days, 60 days, 90 days, even longer, depending upon how long your system is. But sometimes things happen and systems fail. So the ability on the third bullet here to quickly react to those problems is key to power monitoring. And fixed monitoring is extremely important. So something goes down, you need to know, A, was it a power problem? Because sometimes it isn't. It could be an IT issue, a server issue, or something else unrelated to power, just an equipment failure. And if it is a power problem, it gives you that information to understand what happened and possibly where it originated. So this is the key stuff, lets you get back up and running much quicker. So when you're proactively power monitoring, usually on a fixed basis, you can rewind that DVR and go look at this information. If you're not monitoring and you pull out one of our portable tools, like our HDPQ Plus, you're going to connect it, hope the problem happens again. This time you'll capture it. So you're in effect using your systems as an alarm for your power problems. You don't want to necessarily be there if you don't have to. So being proactive can save you money, save you downtime, and prevent a lot of these problems from occurring potentially. So, okay, excuse me. As an introduction to power quality, first we're going to talk about two sources of problems, and we're going to lead up to directivity of power problems. So when we talk about directivity, it's going to be no matter where we're monitoring, we're going to give you some tools to understand how to determine if a power problem, an RMS measured power problem, is upstream or downstream from your monitoring point. But conceptually, it's very easy to look at the point of common coupling with the utility to understand that. And one of the reasons are that's where the utility's responsibility ends and the facility owner's responsibility begins. That's a good line of demarcation, because upstream from that point is the utility's responsibility. Downstream is the facility's responsibility. So the facility manager, the contractor managing it, whoever manages that facility, that's their responsibility at that point. So if I'm measuring at this particular point, which is one of the most common points to measure for power problems, certainly if you don't understand its source, I can easily know and I can easily detect upstream or downstream. All right. So, what happens on the upstream side in this case for the utility? What can happen? Well, you can have just equipment failure, but you have lightning, those power factor correction caps we spoke about at our last presentation, faults, switching, impact from other customers can be a severe issue that you can potentially have. Well, conversely, what can happen downstream? Well, virtually anything can happen downstream in the facility. But you tend to have individual load characteristics, motors, adjustable speed drives, computers, microprocessor controlled things, wiring, changing loads. So any type of load that you have downstream or wiring can become the potential for an issue. So it's important to understand these references here, because we're going to be referencing them later. So we're going to do our first poll question, and let me pop up the poll. Just bear with me a second here. So the question to you folks is, who's responsible for most power quality problems? Is it the electrical utility or the end user? So we're just going to give you folks a couple seconds to respond. So I put in my own vote there because I have my phone connected here as well. So we've got about 43 responses. We'll just give it another couple seconds here. We'll cap it out at total 30 seconds for the poll, and which is right now. So thank you. Let's end the polling. Let's share the results. So here are the results. So 92% of you thought that it was the end user, and 8% thought it was electric utility. Well, those who said end user are correct. Let me stop sharing the results here, and let me close the poll. So it is the end user. Typically about 70% of all power quality events are generated within the facility or by the end user. Now that of course means that the other 30% are the utility's responsibility, but statistically speaking, it is the end user that's responsible for most of the problems. It doesn't mean the utilities, is infallible and they won't have issues, but utilities often spend a lot of time working with their customers on, first of all, identifying the source as being the utility or the end user. And some utilities are very proactive and in fact own our equipment for customer management and the marketing aspect of their company. So, and they will even go in sometimes even free of charge and assist their customers in their facilities to help understand the problems. So you need to contact your utility in such situations to see what type of support should you have issues. Okay, so what are the power monitoring references and terms? As I mentioned before, I used the term geek. This is going to probably be the geekest that we're going to get here as far as the slides and the technical nature of these. But it is important to look at this. So we're going to actually divide this up regionally a little bit. But first we'll talk about the two different standards bodies that are the root of a lot of these standards. And we have the IEEE, the Institute of Electrical and Electronic Engineers. Ironically, one of their main campuses here is about 15 minutes from where we're sitting in Piscataway, New Jersey, just bordering Rutgers University Engineering Campus. So the IEEE defines recommended practices for use mostly in the United States. There is some application in Canada, in Latin America, and in other parts of the world, but it is mostly a US series of recommended practices. Then there's the IEC, the International Electrotechnical Commission. It's European-based, Swiss-based, I think, but their standards are mostly applied in Europe, Asia. They're in Canada now, they're in Latin America, they're being followed in Mexico as well. We see a lot of purchases of our portable products because they're Class A, and we'll speak about that in a few minutes in Latin America for that. So, when you compare and contrast the two, again, there's a regional aspect with the U.S. Following the IEEE, and then internationally outside the borders of the U.S., there's a lot of following for the IEC. So what are these standards that we're going to talk about? So in the IEEE, there's 1159, which is a power quality standard. It is basically a definition of terms. Some of those terms that we're going to discuss later on during this presentation come from the IEEE. So what is a SAG? What is a transient? There's harmonics. There's IEEE 519-2014. What that 2014 means is that its last major revision was in 2014 for harmonics. So primarily we'll focus that on the next presentation a week from today on the harmonics, but that does come from the IEEE. We have a voltage flicker standard, IEEE 1453, that was done in 2014. Voltage flicker is not like a sag or a swell or an increase. It's a perturbation, almost like a modulation. If you picture AM modulation from our school days and ancient radio now, that's what voltage flicker looks like. And there's also a fairly new power standard called IEEE 1250, which kind of takes this terminology and applies them for usage and standards together with applications, almost as a reference document. So now the IEC is interesting, and I'm going to fold this back into the IEEE stuff. The IEC came out with a standard called IEC 61000-4-30. That was roughly about 17 years ago. And one of the big differences is that when we talk about the IEEE, they are recommended practices. No one's telling us in the United States or other places that we have to follow these things. It's just good practice to do it. Well, the IEC came out with their standard that's actually It's required in a lot of applications within Europe and in other places. So it's not optional. It's built into government regulations. Well, 61000-4-30 is now in its third major release, which was done in, I think, around 2014, 2015. And it really defines, what is a power quality problem, how you measure for power quality. So unlike the IEEE up until that point, it says not only, what do I have to do, but here's how we have to do it. So these are the algorithms, the windowing, the bandwidth, the math behind how manufacturers like Dranitz would measure power quality issues. So, and there are a couple substandards involved with that. One is 61000-4-7 for harmonics, and another was 61000-4-15 for flicker or voltage fluctuation. So they not only defined what these things are, they said, here are the guidelines on how to build an instrument to do it. Now, they don't tell us, what our ICs are, how to do the measurements. They just give us the math requirements behind it and other aspects of it behind the requirement. The latest version also has a separate testing standard that actually tests instrumentation to the requirements of edition 3 of 61000-4-30. Now, what Class A means, it means it's in full compliance with this standard. It means you have repeatability of measurement. That's the base need for 61000-4-30 as identified, is that there was an age-old problem in the power monitoring industry where you didn't know who to trust. You put two instruments in parallel measuring the same thing, and they can potentially give you two different answers from different manufacturers. So this leveled the playing field, and it defined the techniques. But the last edition, edition 3 of this standard, has a parallel testing standard that not only looks at the techniques, but says, here's how you test to that. So you get a certification as a result. And if you look at our website, our Dranitz HDPQ data node, our HDPQ Plus family, our PQ3K and our PQ5K have test certifications that we are compliant with edition 3 of this monitoring standard. Okay, so that's very important. The IEEE is catching up to this, and what they've been doing is harmonizing to this. So you can see the IEC has been creating this standard and evolving the standard for 17 years. And so the IEEE basically said, I think, is, well, the IEC does things right in regards to the measurements, so we're going to harmonize to a lot of that. So if you look at this flicker standard, IEEE 1453, it is based upon the IEC voltage flicker standard. The harmonic standard 519-2014, its measurement requirements are based upon IEC 61000-4-7. Again, we're going to discuss this at our next week's presentation. But what the IEEE did is they added some other parameters to that basic measurement where they departed a little bit. But the foundation of the measurements are the same. It's the results and the statistical analysis is where it's a little bit different. So that's really the two standards that we tend to follow. So as a rule of thumb, in the US, you're looking towards the IEEE recommended practices. In Europe, Asia, and other parts of the world, it's typically the IEC or some derivative of the IEC and or the IEEE standards. You'll find, as an example, in China, I believe it's called the GBT standards, which are derivative of the IEC. A lot of them, it has a lot in common with the measurements. Sometimes it's differences in compliance. Just as a point of reference for the folks from Europe who are joining us, you may be aware of EN 5160, 50160. So that's a compliance standard looking at the quality of supply, specifically in Europe, which, it's a little country dependent now, but it really means that it's a utility-based standard. Is the utility within limits 95% of the time? And there's I believe 7 parameter groups, and it's a pass-fail kind of analysis that occurs over 1 week. Again, focused on Europe, but it does have a following, and there are derivatives of that within Europe and also other parts of the world. So what does this boil down to? And really it boils down to, why should you care? I mean, that's the whole thing. We talked about the kind of the geek stuff, as I said, and these standards, but really, why do I care about these standards? So again, I mentioned the industry challenge, the consistency and the repeatability of measurements. So when you have a Class A, certainly edition 3 Class A compliant instrument, you can have confidence that it's going to appropriately detect and report the issues, basically, can I trust the data? Okay. It implies that you're getting the data from a reputable manufacturer and their products have repeatability of measurement. So the folks in the United States would say, well, how does that apply to me? Well, there are two ways how it applies in the United States, or quite frankly, any other country or region that follows the IEEE standards. Well, you get the whole industry repeatability of measurements, but the IEC measurement methods are applicable in the US without any compromises. So you're not taking away, you are adding. However, as I mentioned on the previous slide, the IEC is, I'm sorry, the IEEE is harmonizing with these IEEE standards, IEC standards, I apologize. So you have that future proofing of the capability. So as the IEEE evolves in their recommended practices, which does happen at a slower pace, you know, you can rest assured that for the most part, they're being based upon industry standards that have been used by the IEC for many, many years. Okay, and we of course will adapt as these things evolve, but it's very simple for a manufacturer who provides IEC compliant instruments to adapt to these IEEE requirements if they update their instruments, and that's a big F. Okay, so as an example, in the United States, when you look at the compliance standards, are starting to call out IEC compliant monitoring instrumentation. So a big example in the United States is IEEE 1547, which involves DERs, or distributed energy resources. And this is the interconnection of DERs, which are wind farms, solar farms, any other alternative energy, the interconnection of those to the grid. And they already refer to monitoring based upon IEC 61000-4-30. And we understand future revisions will become more ingrained with the measurement capabilities of the instrumentation being used to monitor. So there's a whole thing of interconnecting to the grid to make sure that's a reliable power source and it's not creating power issues for the utility, or vice versa, actually. So they're defining standards to monitor, and we're referring to industry standards to monitor for these things. So hopefully that was understood. I know it takes a little bit of time to get through that, but hopefully everything's clear. And again, chat up your questions if you have any questions during here, and chat to everyone, and we'll try to address them as we speak here, or certainly no later than the end of the presentation. So now to the meat and potatoes of this. So let's look at the types of power quality disturbances that we have. And these are as per 1159, and these terms have been defined many years ago. And by the way, the IEEE, the one major thing that they're lacking is the overriding standard, like 61000-4-30, which has several substandards to define harmonics and flicker and other aspects to give you a well-rounded picture of a power quality measurement concern, where the IEEE has basically broken it down into substandards, but they don't have a top level standard. 1159 started as that, insofar as terms and conditions of power problems, but they haven't called out those other measurement standards as the IEEE has. So using the 1159 references and names, and these are pretty much renowned worldwide, you have transients, RMS variations, waveform distortion, which are harmonics, voltage fluctuations, which is that flicker that I talked about, and power frequency variations. These are the main issues that most people are looking for. There are other things like imbalance, IM imbalance, unbalance, meaning UN unbalance, and different power parameters. But for the most part, we're looking for these issues when we talk about power monitoring. What we're going to focus on today are the first two, are transients and RMS variations. And as I've mentioned several times, we'll speak about the harmonics in our next presentation. It's a big enough discussion, or long enough discussion, that it made sense just to separate that into its own presentation. So, okay, so our second poll question here: which of these PQ problems occurs most frequently? So just give me a moment to put that up. Let me just choose our second poll questions and launch the poll here. So you folks should see this. So which of these power quality problems occurs most frequently? Is it transients, a voltage swell, which is an increase in voltage, a voltage sag or a dip, which is a temporary decrease in voltage, or an interruption, where voltage just does not occur anymore? So it's basically at or near zero. And we're going to define these terms in a few minutes if you're unaware of them. So again, we'll clip it at 30 seconds. We're at 25 or so right now. We've got about 50 of you are responding. Okay, so we'll share the results. We'll get a last couple in there. We are ending polling, and let's go share the results. So, okay, so 69% of you said it was the an under voltage or a voltage sag or dip. The next highest was transients at 26%, and no one thought it was a voltage swell, which is good, and interruptions was at 6%. So let's go see what is the right answer. So it is a voltage sag or a dip. All right, so statistically speaking, around 2/3 of the power problems out there are under voltage situations, a voltage sag or a dip, which is the same thing, just different regional terminologies. So these are the things that, of course, occur most frequently, but the other things like the transients and the harmonics are certainly a concern for us. So let's go through this list, and we're starting with transients, and then we're going to go to what we call RMS events. And we're going to start from those that occur the fastest in time or over the shortest duration, which is a transient, and then we'll go along and talk about the RMS variation. So what is a transient? We'll see a picture of this in a few minutes, but it is a momentary and, of course, undesirable high frequency event. So excuse me a second. I'm going to mute you 1 second here. Okay, I apologize, folks. I see the poll still up here, so we want to turn off the poll. So let me go look. Stop sharing results. Okay, I apologize. I just happened to notice on my phone that the poll was still there. Okay, all right. So what is a transient? It's a momentary high-frequency subcycle event. And what we mean by subcycle, it is less than one AC cycle. Usually we're talking a quarter of a cycle or less. And of course, a cycle is 16 milliseconds here in the United States and 20 milliseconds in Europe, or whatever the terminology is, but it's usually 50 or 60 hertz. So it's usually measured in microseconds or a few milliseconds. You may also hear terms like a spike or surge or impulse, but IEEE officially call this a transient, but you'll see it under some other names. So instead of going through these characteristics, it's much easier to just see a picture of it. So what are transients? Again, they're just changes in the voltage. And so there's kind of several terms involved in this. So we're going to go through some basic terms. So the first term is what is a positive transient versus a negative transient. So let me first start by what it is not. A positive transient is not a transient that occurs in the positive half of the waveform, and a negative transient is not one that's in the negative half of the waveform. So positive transients add energy to the waveform. Negative transients take away energy from the waveform. Okay, so they can be just as effective, or can affect your system's negative transients just as much, but they're not going to blow something up. So a positive transient may blow something up. A negative transient, for lack of a better term, may lock something up. So you could see here is a positive transient rather, but also here's a negative transient that happens to be on the positive half of the waveform. And again, another positive transient here that's on the negative half of the waveform. So the next thing is, what's the difference between a unipolar and a bipolar transient? So a unipolar transient goes one way. It either goes up or it goes down. That could be negative, that could be positive. A bipolar transient goes up and down. So it goes both ways. So it'll go up and down, and maybe it may oscillate. So this is a bipolar oscillatory transient here. So you can see it goes down slightly, goes up, and then it oscillates here. This is probably from a power factor correction capacitor switching in, which officially is called a negative going bipolar oscillatory transient. That's the official kind of geek term for it. So you also have notching, maybe from a pulse rectifier. You see it's carving out little sections of the waveform here on a periodic basis. Every wave shape would look just like this. Then you have multiple zero crossings. Now, multiple zero crossings are interesting because it's a transient, but it can also affect other measurements that are done or other things that are done within the facility. And what I mean is that there's still a lot of basic circuits out there that that count time or clock based upon zero crossings or transitions. So they're counting your frequency. So what I mean here is that, and a lot of times it's positive going, negative to positive. So I have one zero crossing right over here, okay? I have another one, I have another one, I have another one here, but you see, I counted an extra here. I counted an extra here. So if I'm counting time, certainly here in the United States, 60 hertz works out well for time. I've just counted 2 more clock pulses here. So my circuitry is going to miscount because of these transients. So it sounds basic, but it still is a real problem. And I know I did a seminar several years ago, and one of the power quality engineers from the utility had a digital clock next to this, next to an air ionizer. And so that digital clock, if you can imagine an old digital clock, has that colon that blinks in between the hours and the minutes. And it was blinking at a second rate, which was counting the seconds. When that air ionizer was turned on, it was going nuts and it was blinking at a much faster rate because that air ionizer was creating these multiple zero crossings, which was counting the clock or causing the clock to count faster. So you could see that as a visual difference. Now, one thing that I did not point out before, does not add up to a real, this is not a real survey here. This is just us putting things together so we can define these terms, okay? So what are the causes and effects of transients? Well, they can be caused by power factor correction capacitors. Lightning strikes are a very common cause. Loose connections, just that vibration from a loose connection can cause transients and other problems. You could have load sourcing or switching, things turning on, things turning off, RF bursts, then there's multiple other causes for transients. What are the effects? Well, data corruption, equipment damage, data transmission errors, intermittent equipment operation, reducing equipment life. Most importantly, irreproducible problems. Sometimes transients are very intermittent, so it's hard to predict when they're going to happen. Sometimes they are very predictable, but other times they're like ghosts, and you need power quality instrumentation that's continually monitoring to kind of capture these things, because you may see the effects on your power systems, but it may take a little bit longer to capture the cause of those effects. So continuing along, what is an RMS variation? So we're slowing down here. Now we're talking about one cycle typically, even though IEC 61000-4-30 and some of the other standards say we increment on a half cycle. So what we do is we look at one AC cycle and we increment one AC cycles with, but we advance by 1/2 of a cycle. And then we advance again by 1/2 of a cycle. But we're still looking at one cycle, just the measurements by the instrument are incrementing 1/2 cycle at the time, or at a time. That's the resolution of the measurements that you're getting. But what is an RMS variation? Well, it's a change in the RMS voltage. Again, what we were looking at before showed the AC waveform. So we're not talking about the peaks, we're talking about the RMS of one AC waveform. And it's typically beyond 10% of nominal, and we'll give you some rules of thumb for that in a few minutes. But basically, a reduction in voltage is a sag or an interruption in US terms. It would also become or be classified as a dip in some of our European or other international country terms. So a sag is a reduction in voltage, an interruption is voltage no longer exists or is very low, and an increase in voltage is a swell. So again, we are talking about the RMS. You take all the samples from one AC waveform, whether it be 60 hertz or 50 hertz, and you compute the RMS from that. So the example that I give here in the United States, it's 120 volts RMS when I plug into the wall. In Europe and other parts of the world, it's 230 volts RMS. It's not the peak of that that's used as a reference. So here's some pictures here. This is, again, even though we're referencing the peaks, we're computing based upon the RMS. So we have a sag or a dip, which is a reduction in voltage, a swell, which is an increase in voltage, and an interruption, basically voltage doesn't exist anymore or is extremely low. So this is a 3-cycle sag or dip. This is a 3-cycle swell, and this is a 3-cycle interruption. So this is what the metering or the instrumentation is doing for you. It's looking to see that it crossed a limit that either in Adranet's terms, that the instrument automatically set up for itself. So it's looking to see if it crossed a limit, a high or low limit, and it's measuring the amount of time that it's been out of limits until it returns back to normal. So what are those limits and what's the references that we're talking about? And this is defined by the IEEE, but a lot of people use these rules of thumb and references. So what the IEEE does is they have a table in the standard, and it defines the time range for an event as instantaneous, momentary, temporary, and long duration. And what that means is that instantaneous is 1/2 cycle to 30 cycles in duration. Momentary is 30 cycles to 3 seconds in duration. Temporary is 3 seconds to 1 minute in duration. Long duration is beyond 1 minute. I don't know when it's going to restore back to normal. Okay. And a sag is anywhere from 10% to 90% of what it should be, or 0.1 to 0.9 of per unit. So as an example, on an arbitrary 100-volt system, a sag is from 90 volts down to 10 volts, from 90% down to 10% of the nominal, and that nominal is 100 volts in this example. So what is a swell? It's the opposite sort of case. So it's 1.1 times the per unit, or 110% of what it should be. So in my arbitrary 100-volt system here, a swell starts at 10% above nominal, or 110 volts and higher. So what is an interruption? Well, that is, in IEEE terms, it's less than 10% of nominal. Okay, so it's basically, I go down, a sag is to 10% of nominal. When I go less than 10% of nominal, that's characterized as an interruption. And for all intents and purposes, voltage does not exist anymore. So the IEEE basically says that, you know, the instrumentation and you should report on the duration of an event and a magnitude of the event. So as an example, on my 100-volt system here, if I have a reduction in voltage to 75 volts for, I'll call it 1 second, that would be called a momentary sag. And the reason being is 1 second falls into this momentary category between 30 cycles and 3 seconds, excuse me, and a sag is, it's 75% of nominal, which falls, which what I gave as the example, which falls in this 10% to 90% of nominal. So if you don't remember this, the instrumentation provides this information for you as a summary on the event detail pages. Certainly when we're talking about our HDPQ Plus and SP family, it's provided for you automatically. So really, that's a good rule of thumb. However, what I said before doesn't apply to you and your application specifically. So how do you set up your power monitoring instrumentation? So the first thing, as a point of reference for your limits, a high limit and a low limit, well, you should really look at your equipment specs. And what I mean by that, the IEEE's rule of thumb is plus or minus 10% of nominal. So let's say hypothetically I have a UPS system, and my UPS system regulates my voltage output to 5%, plus or minus 5% of nominal. Well, if I set up my monitor at plus or minus 10% of nominal, it's not going to trigger or record until I've exceeded the specs, that plus or minus 5% specs of my UPS system. So that's probably not a good thing to do. So what we recommend is you set your power quality instrument, your HDPQ Plus or whatever it is, to the weakest link in your chain. So in this case, you set it to the tolerance in our hypothetical UPS system. So you set the output, set the triggering at plus or minus 5% of nominal. If you have a VFD, I'm making these limits up, that is out of specs at plus 5 and minus 10% of nominal, we would recommend that you set up your power monitoring instrumentation to match that. So you know the power monitor is going to trigger at that same point you are out of specs for whatever system or items that you are monitoring there. However, if you don't have those specifications available, then certainly use this plus or minus 10% that the IEEE recommends. And quite frankly, our instrumentation automatically sets itself up with those limits. So in our portable HDPQ Plus, when you choose the automatic setup, as an example, in a 120 volt system here, it'll automatically set it up to 108 volts as the low limit, and 132 volts is the high limit, which is 120 volts plus or minus 10%. However, with our HDPQ Plus, you can also manually enter these things. So when you go into the manual wizard setup, it'll automatically still choose the plus or minus 10% of the nominal that the instrument automatically detected or you programmed into it, but you can override these. You just simply touch any one of these fields and you enter in any number that you'd like. And if you're going to do the same for A, B, and C, you do A and then you copy them over to B and C. It's very easy to do. So again, the moral of the story here is set the instrumentation up to match the tolerances of the equipment that you're monitoring, and you'll get the best results. So we have two PQ rules here before we get into our case study. Now this is on the directivity of the SAG that we're going to talk about. And if you go back to the beginning of our PQ discussion here, we talked about the point of common coupling with the utility. So measuring at that point is very easy because it's that line of responsibility we're determining. So if something goes wrong in your facility, you don't know whether it originated, you may not know whether it originated within your facility or came from the utility. So monitoring at that point of common coupling gives you that information. So you need to determine whether the problem occurred upstream from that point or downstream. Certainly here, but any place that you're monitoring, it's important to know that. So if you're monitoring at the terminals of your motor or device, knowing that it's downstream or upstream is important, but when it's upstream, you still may not know it's within your facility or it came from the utility. So if you monitor at your point of common coupling, you'll have that information. So what are the basics in determining the directivity? So for a source generated or upstream SAG, the current usually decreases or goes to zero. So think of it this way: no voltage, no current. If you don't have voltage, you have nothing to draw current on. Okay, so think of protection opening up, permanently or temporarily, as we'll give in our case study here as an example. So you can see both the voltage and the current are going down. Follow the slope of these waveforms. It could be permanent down to zero, or it could be something temporary, like an instantaneous sag or dip, or a momentary sag or dip. So when you see them both go down at the same time, that is an upstream event. It happened for the source of supply. So in our example, at the point of common coupling with the utility, that is a utility sourced issue. You look upstream there. If it's at the terminals of your motor deep in your facility, well, it's still upstream. You just don't know if it's your responsibility or the utility. So the opposite situation for a load generated sag, the current usually increases significantly. So you will see the voltage go down. You can see the voltage going down, but the current going up. In this example, you can see the current goes from zero and has a relatively high inrush. And if we follow this down, you can see it's reaching its steady state situation. So when you see the voltage and current inversely proportional to each other, that is typically a load generated sag. So in this case, think of a motor turning on. Maybe this was a chiller. We have the air conditioner running on our roof today because it's a very humid day here in New Jersey. So think of that compressor turning on, or the fan, or whatever, the combination of the both. You'll go to a very large current, which pulls down the voltage. So they're in opposite directions, okay? So again, if it's a source generated sag, the voltage and current go down at the same time. If it's a load generated sag, the voltage goes down, the current goes up. They're inversely proportional to each other. So good news, bad news here. The bad news is that you may forget all this by the time we're done with our web presentation today. The good news is that on our HDPQ Plus family, that our guide level, our Explorer and Explorer 400 level instruments have what's called answer modules, and we have a SAG directivity answer module in there. So everything but our Visa level instrument will automatically detect this directivity for you. So if you're monitoring both voltage and current, in this case, it would say this is a downstream SAG and give you the details of the SAG, how long it was out and its magnitude, or an upstream. So it'll put it in right in the data stream. So you don't have to remember, these rules of thumb. Okay, if you're using our Visa level instrument, that's entry level, you have to remember these rules. Guide and above, it'll provide that. And we also have these abilities with the SAG directivity answer module in our fixed systems, in our PQView DE and our PQView software. Okay, let's wrap up here. We're just about on schedule for a five after end time, which is when we started. Now, we'll take questions at the end, Thurman, because we're almost done here. I see Thurman asked if we wanted to take questions now. So if you don't mind, let's roll through this. This will be a couple slides, and then we'll grab all the questions. So we mentioned Hurricane Sandy. This is 2012, about 8 years ago, and you could just see some of the destruction. This is a before of the New Jersey shore, very nice beach line, and this is the after. So this is a big event for the entire Northeast, but specifically New Jersey. And there's a picture of a roller coaster that used to have a pier underneath it that dropped into the water. So it's pretty devastating. So why are we talking about this? You can see this track go right through the southern part of New Jersey. If you're familiar with the United States, this is around the Atlantic City, New Jersey area. And we are north of that. We're, I don't know, 75 to 100 miles north of the Atlantic City area, kind of in the middle of the state. Okay. So it did affect us. It affected us personally at our homes. But this is the power results that we have. This was taken by our Encore series, and we've got other instrumentation that measure this. And again, we're looking at the PSE&G, public service, electric and gas utility feed to our building during this time. So just to set this up a little bit, we are looking at the voltage on phase A, the red phase A here. We could have just as easily overlaid B and C, looked at the currents or any of the other power parameters that we're talking about. So what you're looking at here is the minimum, the maximum, and the average. The thin lines are the min and the max. The thick line is the average. These markers over here on the bottom are event markers. And what it means is that at that point in time, the system recorded an event, or this instrument, this monitoring instrument recorded an event. You may or may not see it here because it may not be an event that you're displaying at the moment, but you could see it recorded events at that period of time, and you could see there's a plethora of data that was recorded here. So this is a Monday morning when data went out, when the power went out. 2 days later, on the 31st, that's Halloween for us in the United States, power was restored. So let's look at that. There's 2 times that we're going to look at. We're going to look at this interruption that occurred earlier in the day. I think it was 2:30 in the afternoon. And this is the long duration interruption that we saw when power went out, I believe about 6:30 p.m. on that day. So when we zoom in a little bit, you can see this is at right over here. We had an interruption. You can see the voltage go down to 0. And then later on in the day, which we'll focus on too, is where we lost power permanently for the next 2 days. So at that that interruption, that short duration interruption, it was at 2:02 p.m. Okay, you can see on top here. Let me set this up. This is the RMS trend of the data being recorded. So each point here is the RMS of one cycle that was monitored by the instrument. Down below here is the oscillography. These are the waveforms that were recorded. Just note that the waveforms in this RMS trend are not synchronized here, so they don't line up because there's different amount of data that's recorded. But what you can see here, you can see a sag or an interruption in the C phase and a corresponding swell in the A and the B phase. So you can see C goes down, and you can see it's opened, it's kind of floating there, and A and B increase at that time. That's the RMS trend. And these horizontal lines here, that's the high limit that the instrument's monitoring, and that's the low limit, which I believe is plus or minus 10% of nominal. And you can see right here where it was before that event particularly happened. So you can see here's the wave shapes before it happened. This vertical line marks the point in time, the trigger point. So you could see C shorted or opened up, or probably shorted in this case. No, not probably, it did short in this case. You could see A and B swelled at that particular time. This is a very typical for a reclosure operation, a utility reclosure operation here in the United States, where one phase shorts and the corresponding 2 phases swell. So what you see here is you could see the short happen on C, A and B swell for about 2 to 3 seconds. Then the reclosure opens up and says, hey, I got a problem here. For safety reasons, I'm opening up. About 10 seconds later, it closes. All these reclosures out on the line do the same thing. So those that can close and stay closed are fine. Their circuits resume normal activity. Those that close and the short remains, those open back up and they clear that fault from the system that way. That's the way it would happen in the United States. So you could see the data from this. You could see this going out 2 or 3 seconds later and resuming normal about 10 seconds later. So it was about 12.73 seconds. This was an upstream temporary interruption was the category. Again, it happened a little after 2:02 in the afternoon. So the final event that happened, and this is very interesting here, this happened at about 6:30, 6:31 and 56 seconds, was our long duration interruption. So you could see here are the limits of the instrument. A, B, and C are within nominal. You could see here's the trigger, and you could see B and C go away, but phase A does not. So you could see that in the oscillography here. You can see everything's fine, everything's normal. B and C sag and then ultimately go away. This is the beginning of them go away. The post trigger was not long enough in the instrument to see that, but phase A remains. We got single phase by the utility. And what that could mean is either they had a protection problem or maybe only 2 out of the 3 wires disconnected, from a utility pole, and phase A remained connected to us. All right, so this could be very damaging for equipment and motors and stuff that are still operating. We of course knew the hurricane was coming, so we shut down our plant that day, so we didn't run a risk of single phasing a motor. But this could be very damaging for a motor. This could be a safety issue as well. So think of in your facility, if maybe your lights and other systems are powered from B and C, and you think that they're off, but you have other devices that were powered by A and they're still energized. If you didn't take proper precautions and you thought you had power disengaged and someone touched that without wearing gloves or turned off the breakers or the protection, there could be a safety issue that was introduced as a result of this. So again, summarizing our voltage variations and sags and swells. So what are the causes and effects? Well, you can have a sudden change in load current that can cause a sag or a dip. When the current goes up, the voltage tends to go down. The power source is not stiff enough, and we see those sags. So picture maybe a lot of things turn on at one time. You could have a very deep sag that can create problems in reset equipment and cause other problems. So you could have a fault on a feeder, a fault on a parallel feeder. This is kind of what we saw before in our hurricane case study, and a whole bunch of other stuff. Those loose connections can cause voltage variations and different things like that. Well, what are the possible effects? A lot of them overlap with the transients that we spoke about. Process interruption, data loss, data transmission errors, PLC or computers to misoperate in both in an office, but of course in manufacturing and a type of environment. And you can just damage products by this that are unprepared to handle this. So these can be very bad situations that can occur. So we're going to wrap things up here. And if you recall, the last presentation, we had an energy savings light bulb or energy savings lighting side-by-side comparison where we compared the energy consumption of a 60-watt incandescent bulb to its equivalent 60-watt light output, compact fluorescent, and LED bulbs. And we demonstrated the cost savings or the energy consumption savings, but we left you with a little cliffhanger. So are there any PQ concerns over that? And we're going to leave you with another one to some extent here. So the answer, you can only answer these questions here. Okay, so let's just look at the wave shapes taken, recorded by these devices. So here's the incandescent bulb in red. And this distortion here is just probably stuff on the power line that's in the lab that we did these measurements. It's probably, well, it's not caused by that light bulb. It's just power or noise on that power system. In green is the compact fluorescent bulb, and in blue is the LED bulb. So really the question is, and we're going to ask that in a second, are there any PQ concerns? And if there are, what is the concern? So let's do our last poll here. Just bear with me. Okay, so the question is, are there any power quality concerns with this? So we'll give it a couple seconds that you guys can answer this question. Okay, so it's a yes or no, simple yes no question. We'll give it a couple seconds. Okay, and then the second question that you'll see when you answer the first, what are the concerns? Are the concerns harmonics, neutral currents, overheating, or all of the above or none of the above? Okay. So we'll give it a couple more seconds this time because we have a two-part question here. Okay, we'll cut it off at 45 seconds. We're at 40 seconds here. So if you haven't answered, please do so. Okie doke. So let's end polling here. We'll share the results. Okay, so are there power quality concerns? Yes, there are. Okay, the level of concern is a little subjective here. But yes, there are, and a little more than 90% of you, 91% of you got that right. Well, if they are, what are the concerns? Well, the correct answer is really all of the above. Yes, harmonics are certainly a concern, and that's the basis of it, but the results of those harmonics can be neutral currents, can be overheating, and I misspelled none, so it should be none of the above. I apologize. So all the above is the correct answer, but anything above this is correct, okay? And the harmonics caused, so if I just stop sharing these results and I close my poll, if I go back one slide, you can see that even with LED bulbs, there are some harmonics involved. And we'll give you the specifics at our harmonic web meeting a week from tomorrow, or a week from today, rather, on the 13th, I believe. And we'll share the actual details of these harmonics to wrap this up. But you can see there are harmonics concerns. The concern may not be one light bulb. Maybe the concern is multiple light bulbs connected in parallel. So are there concerns? Yes, we'll get into the details of that during our next presentation. So just as a summary here, we're basically all done. The Dranitz products that do power quality monitoring. We have our HDPQ Plus family here with its SP, also another HDPQ family. Our new DRAN Expert, it's primarily an energy and power logger, but it is also a PQ detector, as well as our fixed systems from our HDPQ data node, our 61000 series, to our PQ 3K and 5K, and even our AM series energy meters have basic power quality detection capabilities. So that's about it. Thank you so much. We're going to go look at the chats here. Thurman and I are going to just work in the background, and I'm going to go kind of bottom up here and start looking at the chats. Again, if you have not chatted a question and you would like to, please do so. And we're going to stay tuned here just to go answer the questions. So let's see, the first one here, are there a lot of harmonics interconnection to the utility scale in solar? And because of the change from AC to DC. And Jay asked that question. I'm going to honestly answer, I don't know for sure, but there is certainly a potential for that with the use of the inverters. I think a lot of that depends upon the quality of the inverter and how it compensates for any noise on that from the switching and the high speed on the creating the AC, recreating that AC at the interconnection point. But that's why IEEE 1547 was interested in harmonics, because it is certainly a concern at the point of common coupling. So, okay, Benjamin, hang on a second. I'm going to just mute all you folks. Just bear with me. Someone unmuted here. So I apologize. Was that you, Thurman? Okay, Thurman, you can unmute. Okay, that's fine. Thank you. Okay, so Benjamin asked, the magnitude is more dangerous if it's at the peak of the waveform. And of course, okay, so thank you, Benjamin, for tossing that in there. And then Trent, I don't think this is a question, just a comment. I would say that a spike at the peak would be more dangerous typically, of course. But I can add that a spike, no matter where it occurs, you may not blow something up, but you have the potential to lock something up. So certainly with a positive transient at or near the peak, or something that greatly exceeds the peak, can be not only damaging, but trip breakers, blow fuses, different things like that. But again, negative transients, that's an advantage of the Dranitz products, is that we have the ability to use our wave shape triggers to detect negative transients. And what I mean is, it's fairly easy to detect positive transients because you're looking for a positive peak. Negative transients are more difficult because you're digitizing a regular waveform, and when that value gets reduced, it's hard to separate that from just a normal RMS measurement. So our wave shape triggers compare cycle to cycle. So we could see that this cycle does not have a change in wave shape, and the next cycle does. And maybe that was a negative transient that occurred. So we can detect that. So we have some other comments about constant power loads. We have in the Navy, the current increases when the voltage decreases. Yes, certainly. We have a question from Jamie, if I'm pronouncing that right. Open to everyone. How do you handle an open delta PT setup on medium and high voltage systems? Do you connect as an ungrounded delta? There's some other details here. So I don't think anyone addressed that. Let's see if we can address that. Open delta, oftentimes with our products, can be considered very much like a split phase connection. Whether you have grounded or not, I think that's up to your wiring and what you have available to you. Depends upon where that ground is and if that's actually a ground. So I think a lot of people have high impedance grounds or other things where that may not be an actual ground, so you may need to do that. So some people prefer to measure it as a split phase like, other people like to look at it as a true delta and just consider it one open phase. Okay, so I think Thurman's agreeing with me here. So Trent asks or comments, for me, it's easier to plot KW or KVA as a function of time, as if the power source goes down during sag. That's certainly a very good indicator, Trent. So the only difference in doing that, I might add, is that for very quick events, you may not see a significant change in your KW or KVA. The way the instrumentation works these days is that for what we'll call fast changing power quality events like RMS voltage and current and transients, we're looking at every AC cycle. However, the KW and KVA in most instruments today are measured at 200 millisecond groups. So it's averaged or measured over 200 milliseconds. So very short-term things may not be reflected in your KW or KVA, but longer term beyond that, yes, it's a very good reference to use. So, okay. So Benjamin included, Thurman, did you look at this this image? Okay, so I'm going to ask Thurman to open that image and have a look that Benjamin sent up, and then Benjamin, we'll answer your question then. I think there's two images from Benjamin. So let's just hang on for Thurman here. I'm going to unmute Thurman here as well. Okay, I can't. You have to unmute yourself, Thurman. I can't do it.
All right, I'm unmuted. Let's open our file. Okay, so our file shows your typical transient event, and the question, what does the worst peak to peak mean in the file example, and how should this information be interpreted? So the chart itself shows your typical transient with the positive peak being worse, and so the question is, what does the worst peak to peak mean? Well, it depends on how you interpret it. Some people will use the term peak. Some people will use the term peak to peak. If you're reviewing the overall amplitude of the transient, then you would refer to the peak to peak. So it's a matter of how it's interpreted. Some people, again, will refer to it as peak. You know, for example, 120 volt RMS has a peak value of about 170 volts. But if you went from peak to peak, then you could almost double that. But it depends on how it's being interpreted. How you would interpret it, I should say. Hope that answered your question.
Okay, thank you, Thurman. And I think, Benjamin, you sent something else too. Let's go look at that. So I think the event can also be generated at another system node.
So you want to download that, please, well. Thurman? Yep, yeah. Opening that.
Yeah, and I'm asking Thurman to do it just because I don't affect our meeting by doing that here on my computer.
Okay, so we see, I'm unmuted. So we see in this example here, here we're viewing transient data both from the voltage and from the current. Now, obviously what's going on here is that you have the voltage basically reacting to what the current is doing. Nevertheless, it causes this particular transient. And so now the concern here with this particular event is this peak value. Because and we're looking at the positive portion of it, so the concern is this peak value, is it harmful where it can, let's see if I can share the screen.
I'm sharing it right now.
Oh, you have it?
Yeah.
Okay.
Yeah, I just downloaded it. Okay, just bear with me.
We're also downloaded, I'll narrate it.
Is that it, or is that the other one?
No, it's the next one.
Okay, hang on, just bear with me. When I went to do the share, of course, they both look the same. So it is,
I think with title capture, that's the one.
Is that it? Okay.
Yep, that's the one.
Okay, so got there.
So in this example here, this is obviously this voltage transient is basically reacting to what the current is doing. So your bottom graph is showing your amps, the top graph is showing the volts. You obviously see a transient. And to Ross's point, just when you have a voltage transient, that voltage transient is being caused by the current doing something. So, our instrumentation is capable of capturing voltage transients and current transients. And those PQ rules that you use to determine directivity for RMS events such as sags and swells, you can also use those same rules for subcycle events, current transients as well, as long as you have the instrumentation that is capable of recording, capturing, recording that data. But getting back to this chart here, the concern here is the peak value of the voltage transient. Whether or not that peak value is going to cause something to misoperate or lock up. If this is a common occurrence and equipment is always seeing this transient, then it can lead to premature failures because you're basically just wearing down the front end of that particular device because it's always seeing that transient. So yeah, this would be a concern. And again, it depends on what Ross alluded to earlier about susceptibility. Am I susceptible to events like this? And, obviously if you have the power monitoring instrumentation that's capable of recording this, and the ideal thing that you look for is if you have what we call a consistent correlation to where you haven't recorded event and something happened within user equipment, either something fell or it locked up. And because our instrumentation records the time and date, you can draw that correlation. So if you have that consistent correlation, then you know that is causing a problem. Then the next step obviously is to mitigate it.
Very good. Thank you, Thurman. As Thurman mentioned, a lot of the events are actually caused by current. And you'll see even when we talk about harmonics next week, usually the voltage is not, the harmonics are not originating in the voltage. It's usually current based or load based, I should say. When you turn on those asymmetrical loads or those asynchronous loads, they're generating the harmonics, which is reflecting in the current. So just like you see here, this is some load turning on, and you can see it's affecting the voltage at that particular point. So you'll see there's a relationship between voltage and current here, and it's important to understand that. Not for current, but for voltage, one of the big changes with IEC 61000-4-30 with edition 3 is that current is treated the same as voltage. And in addition to and prior, voltage was only monitored. From a Dranit's perspective, we've always treated current just like voltage, so it was no big deal for edition 3 for us. But it officially says now in 61000-4-30 edition 3 that you shall measure the current in the same way that you measure the voltage. For situations like this, it's for RMS events, but so because of that relationship, you are looking at a closed circuit here. So you will see voltage affect the current and current affect the voltage, and that's what we're looking at.
I should also add finally, Benjamin, that yes, you made a comment that it's not necessarily harmful. Well, again, it depends on what I explained earlier, but there's something that you should always keep in mind, that you can have what we call incipient events, and these are precursor events. And precursor or incipient events can also be indicators of a pending more significant failure. So, for example, if these waveforms that you're recording are worse in amplitude and record more frequently, then that warrants you should investigate why that's occurring. Because very often it can be a sign of a more sinister problem waiting to cause downtime and economical impact. So, just keep an eye on that.
Very good, Thurman. Thank you. Okay, I think we've addressed all the questions. So please, Thurman and I will hang here for a little bit. If we missed your question, I apologize. Please just re-ask it. Or if you have an additional question about this topic or any other topic, regarding to Dranit's products or the industry, feel free to do so. So I'll say thank you right now. Again, Thurman and I will wait for a little bit till we have people drop off to address your questions, but thank you so much. Again, a reminder, our next session on harmonics is next Wednesday. The was it the 16th? I'm going brain dead on that. But either way, go to our website, register the same way that you registered for this presentation, and you'll be able to register for the next one and our last presentation at the end of the month. Of course, we'll be sending out reminders. So thank you so much, everyone, and we appreciate your attendance today, and we'll see you next time, hopefully.